A long time ago, I made a series of videos called Problems in Real Analysis. The reason I made those series of videos is because I wanted something on the channel that I could look over and review in preparation for my qualifying exams. That was pretty much everything I did back then was built around qualifying exams. And now that the qualifying exams are over and I don't have to really review all these problems anymore, there's not much incentives to keep the series going. But I did want to make at least 2 more episodes, because then I'll have 10. And when I had, just because I like the number 10. And I wanted to put them all in a playlist for maybe future viewers of the channel to go back over and look through, and as well as myself. So I want to make at least 2 more before we get too far away from that series, because the last episode I made has been, months ago. I don't remember when I uploaded it, but it's been a long time. And that's what I'm going to do in the next 2 videos. Or at least, hopefully, the next 2 videos. I'm still doing the interviews. So if you don't remember what the episodes were like, I do 3 problems in analysis of ranging difficulty. I start with easy, go to medium, and finish with hard. And it's a little bit subjective as to which problems are harder than others, because it kind of depends upon the person, but I tried my best to arrange them in a difficulty I thought was most reasonable. All right. Well, I almost threw my phone there. Now let's do the first problem. We have a sequence of continuous functions fn. They're defined on the compact unit interval, they are real valued, and they're all continuous. We assume that fn converges to f uniformly, so the double arrows mean we have uniform convergence. Prove that for any sequence xn that tends to 1/2, we have that the limit fn xn, as n tends toward infinity, is equal to f of 1/2. Now, a couple of things go through my mind when I read the first line. The biggest thing is that I have a sequence of continuous functions converging uniformly. Whenever you have that, I believe it's a theorem or proposition in pretty much any analysis book, is that the limit function f itself has to be continuous. So I'm keeping that in the back of my mind when I'm doing a problem like this. How do I invoke the continuity of f in some way? All right, so let's see what the solution looks like. We start at the beginning, so we know that for any sequence xn converging to 1/2, we want to show this. So that means we let the sequence xn be given. So we have some sequence converging to 1/2. And then we let epsilon positive be given. And the reason that, what we want to do with this epsilon is we want to show that if we subtract this guy from this guy in absolute value, that is going to be less than epsilon, and that's true for any epsilon. That is the idea that we want to invoke here. All right, so what can we do? Where do we start? We have uniform convergence, so let's just apply the definition of uniform convergence. So we know that there is a big N, such that for all little n bigger than or equal to n, it follows that fn x minus fx is less than epsilon over 2. We can choose a big N depending upon epsilon that gives us this inequality. And you might ask the question, like, what is x here? X is any value within the compact interval. Because you have uniform convergence, the x can come first before the n. The n doesn't depend upon the x. And we have this inequality. And it's not really obvious like what we're going to do with the inequality right now. And the fact that we have epsilon over 2 here is also kind of like, why are we using it? It will be made apparent at the end. Now, how do we use the continuity of f? Well, the definition says that we can find a delta positive such that for any x and y in our compact interval, if x minus y is less than delta, then absolute value fx minus fy is less than epsilon over 2. We can choose a delta that meets those demands. This comes from just the continuity of f. I think also because everything here is defined on a compact space, we know that we have a uniformly continuous function. But these 2 inequalities are what we're after. Now, because we have a sequence converging to 1/2, we know that there exists some index m out there. We don't know what it looks like, but we know it exists out there, such that for all n bigger than or equal to big M, we have that xn minus 1/2 in absolute value is less than delta. And the idea here is that we want an index big enough such that this is met and that this implies this. And we want to have both of these inequalities. So we have two indices going on here. We have n and m, and we need to choose an index such that we have both of these so that these two inequalities, are at our disposal. And that's where the next line comes from. We want to choose an index big K, and we can set that equal to the maximum of the two. It doesn't have to be those two. It can just be something bigger than n and m. But if we set it equal to the maximum of the two, then we know that we have both of these inequalities. And now comes probably the most famous inequality in analysis, the triangle inequality. So we have fn(xn) minus f of 1/2. We can add a 0 inside, and the 0 that we want to add inside is fxn and minus fxn, so that if you add these two, you get 0. I didn't write it up here, probably I should have, but it was obvious to me at the time what I'm doing here. Because once you have those two values introduced inside, you can split using the triangle inequality to get this guy. And so you have fn(xn) minus fxn, and here you have fxn minus f1/2. And both of these guys can be made small. How do I know this? Because this guy looks like this guy. We can make this less than epsilon over 2. And this guy here is true by this inequality. So x is playing the role of xn, x is playing the role of, y is playing the role of 1/2. So both of these guys are less than epsilon over 2, and if you add these two together, you will get epsilon in the end. This is why epsilon over 2 was chosen up here. If you had just chosen epsilon, then you'd get 2 epsilon in the end, which really doesn't matter. It's just that if you want epsilon at the very end, then you have to choose epsilon over 2 up in the corner. And that's the first problem. So you can see I highlighted a bunch of stuff here. This is back when I was reviewing. This is like maybe a month or two before the second time I took the qualifier, and I was just trying to identify what tricks were involved in these problems and what the general strategy was. I don't know what I was doing. I was trying a bunch of different things. But that was the first problem. I think I got that off of a website somewhere. It wasn't a homework problem or anything. Okay, so what about the second problem? We let mu be some positive measure on a measure space x, and we assume that mu of x is finite. So it's a finite measure space. We assume that f is non-negative on the space x, so it's always bigger than or equal to 0. And we want to prove that f is an L1 function, meaning that it's integrable over the space x, if and only if the series from n equals 0 to infinity of 2 to the n times the measure of the set of all points x such that f of x is bigger than or equal to 2 to the n is finite. And I know I said a bunch of words there and it's not really written down. It's just, this is a shorthand notation that textbooks will use all the time to describe what I said. So you do need a little bit of measure theory to understand what's going on with this statement. And that's the problem. We want to show if and only if. Okay. So this problem seems kind of scary, at least to me. This was kind of a scary problem. But once you see the solution and you have at least a rudimentary understanding of measure theory, you'll be like, oh, that's actually kind of clever and nice. It's a nice problem. And the first thing we do is we simplify the notation a little bit. And we let En denote the set of all points where f is bigger than 2 to the n. And so we're essentially, what we've done here is we've replaced this set with En. So we have measure of En. And we define a new function, gx, to be equal to the sum of 2 to the n times the characteristic function over the set En. And if we define g in this way, we notice that if we integrate g over the space x with respect to our measure mu, then by definition of the Lebesgue integral, we know that this integral is equal to the sum 2 to the n mu of En, which is exactly what this expression is. And what we've done here is we've basically said we will have this statement, we will have the result of the problem that they answer if we can show that f is an L1 function over x and that g is an L1 function over x. And when you write it this way, you're kind of thinking to yourself, why on earth would you, where does this intuition come from? Why would we define such a function gx and take this route? It's not immediately obvious why. And to be honest, I think this is just something that comes with experience and you have multiple minds working on a single problem, because I don't really see how anyone would come up with this trick. Because it's what it is, it's a trick. Analysis is basically, from what I've learned, a series of tricks to show that some things are bounded and other things aren't. But what do I know? I'm just a graduate student. Okay, so that's what our goal is. We want to show that f and g are L1 functions. And what we do here is we start with fx and say, okay, let's say that fx is between two consecutive powers of 2. So it's bigger than or equal to 2 to the n for some n, and that should be less than 2 to the n plus 1. So let's get rid of this. We'll have strict inequality. Try and make it obvious for future me when I'm reading back over it what's going on. So we have fx as bounded between 2 to the n and 2 to the n plus 1. And then we say, okay, if x is between those two values, what is our function g doing? Because g is kind of defined with f in the background. So we know that if f is bigger than 2 to the n, then for n all the way up to, big N, this characteristic function, let me arrange this better. We know this characteristic function will return a 1 every time, f satisfies this condition. And so what we end up getting is we get powers of 2 being added up together all the way up to big N, which is what we have here. And then since f is less than 2 to the n plus 1, it's going to be less than all other powers of 2 larger than that. And what happens is that this characteristic function will return 0 all the time. And 0 times anything is 0, and if you add a bunch of zeros together, you just get 0, 0, 0, 0, 0. And so what happens is that if f is between these two consecutive powers of 2, you'll add up the first, I guess, n plus 1 powers if you consider 0, like 2 to the 0 is a power of 2, which is, true, but it depends on how you want to count. So we start with 1, 2, 4, and we go all the way up to 2 to the n. And then comes an interesting observation, is that it is not too hard to show that this sum can be rewritten as 2 to the n plus 1 minus 1. I didn't do that here because it's kind of a high school exercise. It's not immediately obvious how you can get from here to here. But if you're interested in showing it yourself, what you should do is take this line, multiply it by 2, and then subtract it from both sides, and you'll get an expression. Okay, because I'm annoyed, we'll do it here. This is how I teach, by the way. I say, okay, how about you guys do it, and then I just end up doing it for them. Skip ahead if you already know what I'm going to do. So I don't know what this is, so I'm going to call it S. And if I multiply both sides by 2, I'll get 2 plus 4 plus a bunch of stuff, plus all the way up to 2 to the n plus 1 is equal to 2s. And if I subtract, all these will cancel, except for this guy. So you end up with 1 minus 2 to the n plus 1 is equal to s minus 2s, which is equal to negative s, which means that 2 to the n plus 1 minus 1 is equal to s, which is exactly what we wanted up here. So I make that substitution right here. Now, why do I care about that number? Well, we can notice a few things, that if we add 1 to both sides, then we know that gx plus 1 is going to be strictly bigger than fx, just by using this property if I add 1 to both sides, which is exactly what this line says. F is less than or equal to g plus 1. Now, what happens if we divide gx by 2? If we divide gx by 2, we will get 1/2 plus 1 plus 2 plus all the way up to 2 to the n minus 1, which is equal to 2 to the n minus a half. And if we move that half over here, we can see that this value is going to be exactly, well, not exactly, but f is going to be bigger than 2 to the n, which is what g over 2 is. So we end up with this inequality that shows up here. fx is bigger than or equal to gx divided by 2. So we have two interesting inequalities. We have f bounded below, or excuse me, we have f less than or equal to g plus something. And here we have f is bigger than or equal to g divided by something. And also we should mention that if x is small, meaning less than 1, then gx is equal to 0. So nothing really is interesting happening there. And what this ends up saying is that if we assume that f is finite, or excuse me, if the L1 norm of f is finite, in other words, it's integrable, if f is integrable, then gx has to be integrable as well, because this is a finite number. We can just move the 2 over and get a finite number is bigger than or equal to the integral of g. So g has to be integrable. Likewise, if we assume that g is integrable, then we know that the integral of g plus 1 is finite. Again, this is where you need to invoke the fact that mu of x is finite. We have a finite measure space. Without this, you can't do it. But this integral will be finite, which means that the integral of f also has to be finite. So you get if and only if in one fell swoop, which is what the last line is here. Not really an easy problem, in my opinion, but I thought it was an entertaining solution. I like the solution to that problem. And now we have the mean one. I call this the mean one because this was featured on the channel before. I like this problem. I think it's interesting. And I spent a long time trying to solve it. And it had a trick in it that was so obvious. Well, it wasn't obvious, but it was such a deceitful little trick that because once I saw it, this problem lives rent-free in my mind now. I can recite and prove this problem, on a moment's notice. I'm walking down the street, you ask me to do it, I can do it. So what does the problem say? Gn is a sequence of Borel measurable functions. They're real valued. They're functions of a real variable. We assume that the absolute value of Gn is bounded above by x to the negative fourth on the whole real number line. And we know that the integral of x squared Gn to the fourth over the whole real number line is less than or equal to 1. Prove that if Gn converges in measure to 0, then the integral of Gn also converges to 0 as n tends toward infinity. This was on a practice qualifying exam that I took when I was preparing for the first qual, and my instructor that wrote it said that this one was probably the hardest one on that in that batch of problems that he wrote. So let's look at the solution. Now, the way he did it was a lot faster. Like, he used some really slick tricks to get to the right answer, but he said that my answer also worked, but it's just longer. But I'm more proud of my answer because I came up with a lot of it, so I'm going to present this one. So the first thing we do is we split up the domain of integration into bits that we have some control over. So we set e equal to the real number line, get rid of the interval from -1 to 1. And I choose a neighborhood of 0. It doesn't have to be -1 to 1. I just chose it. Because now, if we're outside some neighborhood of 0, we can apply the dominated convergence theorem, which we know we can apply it because we have this assumption here. Absolute value Gn is less than or equal to x to the negative fourth. Because this function outside a neighborhood of 0 is integrable. So if this is integrable, then this is integrable. And we can pass the limit inside. So you pass the limit inside, and we can see that the integral over e of our functions Gn tends towards 0. So already, most of the real number line is taken care of. Now, we need to look at what's happening on this interval. So we use the assumption Gn converges in measure to 0, the definition of which is the third line. So the definition says for any epsilon positive, there exists an index big N, such that for all n bigger than or equal to n, the measure of the set absolute value Gn bigger than epsilon is less than or equal to epsilon. So we have this set, and I give this set a name just so that, I can save some ink in my pen. I call it A for simplicity, and now what I'm going to do is take this set that I ignored up here, and I'm going to split it into two pieces. So we have the integral gn over -1 to 1. We want to make sure that this integral is small. And the way I'm going to do it is I'm going to split it into the piece that's inside of A and the piece that's outside of A. And the first thing I notice is that if we are outside of A, then by definition of A, the absolute value of gn is bounded above by epsilon. So I can replace this in absolute value. So that's what I'm writing down here. If I put absolute value bars here, then I know that this function is bounded above by epsilon. The domain of integration that we're over is bounded above by 2. This is all a Begg measure, by the way. So we know that the whole integral itself has to be less than or equal to 2 times epsilon. So we can make this as small as we want by choice of epsilon. The only issue, the hard part, quote unquote, the hard part with this problem is showing that this integral is arbitrarily small. And the only thing that we can really control is the set A, because we know that this set is less than or equal to epsilon. So we don't have control over the function so much, but we do have control over the domain of integration. And that's how we're going to proceed. And again, to make notation easier, I'm going to define the domain as the set B. And I want to show that I can control how big B is. Okay, so we have the next line, integral gn over B. We use a trick where the integral of a function over some set is the same as the integral of gn times the characteristic function of B over the set of all real numbers. So it introduces two functions. And then this is the part where I didn't really know what to do next. So my instructor said you need to multiply by 1 in a creative way. And the one in creative way that he introduced was x to the 1/2 power on top and x to the 1/2 power on bottom. Why are we doing this? Because we have an assumption up here, this guy, that was not used. And we need to introduce this x in some way. So now that we've introduced it here, what are we going to do with it? Well, we can apply Holder's inequality. And by Holder's inequality, I want to apply Holder's to this as its own function, and Holder to this as its own function. So for this guy, we want to raise it to the 1/4 power, which means that the integral gets raised to the 1/4 power. So that's what happens here. And then if that's the 1/4 power, you can find the conjugate exponent. But if I'm raising this guy to the 4th power, I'm going to raise this guy to the 4/3 power, which shows up here, which means that the conjugate exponent up here is 3/4, because I want 1/4 and 3/4 to give me 1. So if you raise this guy to 4/3 power, this is what we get on the inside. And this guy here is bounded in absolute value above by 1 by assumption that we have here. And this guy, we can kind of declare victory more or less here if you supply enough details. But this guy is as small as we want because B can be made as small as we want. And if you and the reason that you can make it really small is because if you look at the set containing B being -1 to 1, if you integrate this function over that set, you'll get a finite number. And that's the most important thing. I believe the word is uniform integrability here, which means that if you make this domain of integration small, you make the whole integral small. And you can only do that provided that this function over whatever we're integrating over is finite, which it is. The function x to the -2/3 is integrable over -1 to 1. And I kind of throw in those details here at the bottom, but I think when I presented this to the class, I just said, we can make this as small as we want by uniform integrability. And that's the solution to the problem. This was the hard problem from that practice qualifying exam. And now it lives rent-free in my head. I can more or less do this at a moment's notice. So this is the 9th episode, I know it doesn't really matter, you know, you can do one problem, big deal. A lot of people can solve one hard problem. But whatever, it makes me feel good about myself, so let me have this tiny victory. So this is episode 9. Episode 10 will come out fairly shortly. Thank you for watching.